Welcome to this coding tutorial. Today, we'll be exploring problem number 1038, titled Binary Search Tree to Greater Sum Tree. In this problem, we'll transform a binary search tree into a greater sum tree, where each node's value is updated to the sum of values greater than or equal to its own. Let's dive in. In this problem, you are given the root of a binary search tree, or BST, and your task is to transform it into a greater sum tree, or GST. In a GST, the value of each node is replaced by the sum of all values in the original BST that are greater than or equal to that node's value. A binary search tree has a specific structure. The left subtree of any node only contains values that are smaller than the node's value, while the right subtree only contains values that are larger. Both of these subtrees must themselves also follow the rules of a BST. The transformation must be performed in place, meaning we cannot create a new tree, we have to modify the input tree directly. The input to the problem is the root of the BST, and the output is the modified root after applying the transformation. Let's walk through an example to understand this better. Suppose the input tree looks like this. The root is 4, with left and right children 1 and 6, respectively. Node 1 itself has children 0 and 2, while node 6 has children 5 and 7. Node 2 has a right child 3, and node 7 has a right child 8. After transforming this BST into a greater sum tree, the root node's value becomes 30, and its left and right children are updated to 36 and 21, respectively. Similarly, all other nodes are updated based on the sum of values greater than or equal to their original values in the BST. For example, node 1 becomes 36, node 2 becomes 35, and so on. The tree structure itself remains the same, but the values of the nodes are updated. Here's how the transformation works step by step. For the root node, which is 4, we consider all nodes in the original BST with values greater than or equal to 4. These nodes are 4, 5, 6, 7, and 8, and their sum is 30. So, the value of the root becomes 30. Next, for the left child, which is 1, we look at all nodes with values greater than or equal to 1. These nodes are 1, 2, 3, 4, 5, 6, 7, and 8, and their sum is 36. So, the value of the left child is updated to 36. We repeat this process for every node in the tree. For instance, node 2 is updated to 35 because the nodes greater than or equal to 2 are 2, 3, 4, 5, 6, 7, and 8, and their sum is 35. This process continues until all nodes in the BST are updated to form the greater sum tree. Now, let's look at a simpler example to reinforce the concept. If the input tree has just 2 nodes, with 0 as the root and 1 as its right child, the transformation works like this. For the root node 0, the nodes greater than or equal to 0 are 0 and 1. Their sum is 1, so the root's value becomes 1. For the right child, which is 1, there are no nodes greater than it, so its value remains unchanged. The constraints for this problem are as follows. The tree can have up to 10,000 nodes, and the values of the nodes can range from -10,000 to 10,000. Additionally, all the node values in the tree are unique, and the input tree is guaranteed to be a valid BST. Edge cases to consider include single-node trees, skewed trees where all nodes are on one side, trees with negative values, and small trees with only 2 nodes. The algorithm must handle all these cases correctly. To solve the problem of converting a binary search tree into a greater sum tree, let's first consider the brute force approach. The intuition here is straightforward. For each node in the BST, we calculate the sum of all values in the tree that are greater than or equal to the current node's value, and then replace the node's value with this sum. To implement this, we would perform an in-order traversal to retrieve all node values in sorted order. Then, for each node, we would iterate through this list to compute the required sum. While this approach is simple to understand, it has significant drawbacks. The time complexity is O(n) squared in the worst case, as we perform an O(n) traversal and an O(n) summation for each node. This inefficiency becomes a performance bottleneck for large BSTs due to repeated calculations and unnecessary overhead. Now, shifting to a more efficient solution, we can consider using a reverse in-order traversal. This optimized approach takes advantage of the BST property where in-order traversal produces values in ascending order. By reversing the traversal order, starting from the right subtree, processing the node, and then moving to the left subtree, we process nodes in descending value order. During this traversal, we maintain a running sum, which allows us to efficiently update each node's value to the sum of all greater or equal values. Key observations supporting this approach include the fact that reverse-in-order traversal naturally processes nodes in the desired order, and it avoids redundant computations by using a single traversal. The implementation can be done using either recursion or an iterative stack-based approach, where a variable tracks the running sum and updates each node's value in place. This makes it highly efficient in both time and space. The time complexity of the reverse-in-order traversal approach is O(n), as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, which accounts for the recursion stack or the explicit stack used during iteration. Now, an alternative approach worth mentioning is the Morris traversal. This technique enables in-order traversal of a BST without using extra space for recursion or a stack. By adapting Morris traversal for reverse-in-order traversal, it is possible to achieve the same goal of transforming the tree into a greater sum tree. The primary advantage of Morris traversal is its O(1) space complexity, as it avoids the need for additional storage. However, there are notable drawbacks. This method temporarily modifies the tree structure by altering the pointers, which could be undesirable in scenarios where the tree's integrity must be preserved. Furthermore, the implementation is more complex and prone to errors. While Morris traversal provides an intriguing alternative, its trade-offs make it less appealing for general use compared to the reverse-in-order traversal. Among the approaches discussed, reverse-in-order traversal stands out as the most balanced and practical strategy. It is efficient, with O(n) time complexity and O(h) space complexity, making it suitable for large trees while avoiding unnecessary overhead. The simplicity of its implementation is another major advantage. By avoiding modifications to the tree structure, this method is not only robust but also easier to debug and maintain. When weighing the trade-offs, it becomes clear why this approach is preferred. Compared to the brute force method, it eliminates redundant computations and significantly improves performance. While Morris traversal does offer a theoretical advantage in space complexity with O(1) usage, its complexity and the temporary side effects on the tree structure make it less desirable in most practical scenarios. The O(h) space required by recursion or a stack is generally acceptable, especially for balanced trees where the height is logarithmic relative to the number of nodes. Ultimately, the reverse-in-order traversal approach effectively leverages the properties of BSTs, delivering a solution that balances efficiency, simplicity, and reliability. It is well suited for transforming even large BSTs into greater sum trees with optimal performance. In this problem, we are tasked with converting a binary search tree, or BST, into a greater sum tree, or GST. The idea is to transform each node so its value becomes the sum of all node values in the original BST that are greater than or equal to its own value. To achieve this, we first need to recall the key properties of a BST. For any given node, all the values in the left subtree are smaller, and all the values in the right subtree are larger. This inherent structure allows us to traverse the tree in a particular order to access its values systematically. Typically, an in-order traversal, which processes nodes in the order left root right, retrieves values in sorted order. However, for this problem, we need to process the tree in reverse-in-order order, which is right root left. This ensures we encounter larger values first, allowing us to maintain a cumulative running sum as we go. By keeping this running total, we can directly update each node's value during traversal. Finally, we can implement this idea using a recursive approach for simplicity, as recursion naturally handles the depth-first traversal of the tree. To translate the reverse-in-order traversal approach into an algorithm, we start by initializing a variable called running_sum to 0. This will keep track of the cumulative sum of the nodes we've processed so far. Next, we define a helper function called convert that takes a node as input. If the node is null, we simply return, signaling the base case of our recursion. Otherwise, we first process the right subtree by calling convert on node.write. This ensures we handle the larger values first. Then, we update the running_sum by adding the current node's value to it. The current node's value is replaced with this updated running_sum. Finally, we move to the left subtree by calling convert on node.left. This ensures smaller values are processed after larger ones. Once the helper function is set up, we call it with the root of the tree to start the transformation. If recursion and stack space are a concern, we can also use an iterative approach. This involves using an explicit stack to simulate the recursion. Starting with an empty stack in the root node, we traverse the right subtree by pushing all right nodes onto the stack. Then, we pop the top node, update the running underscore sum, and replace its value. Finally, we move to the left subtree. Both the recursive and iterative approaches leverage the same underlying logic, ensuring correctness and efficiency. The reverse in-order traversal is at the heart of this algorithm. By visiting nodes in descending order of their values, we can calculate the cumulative sums directly during traversal. This eliminates the need for additional data structures or pre-computations. Another key insight is that we update the node values in place. This means the transformation is done directly on the original tree, avoiding the need for extra storage. For scenarios where recursion depth might be a limitation, the iterative approach provides an alternative that uses a stack to manage the traversal explicitly. This reduces the risk of stack overflow while maintaining the same time complexity. Speaking of complexity, the time complexity of this algorithm is O(n), where n is the number of nodes in the tree. Each node is visited exactly once. The space complexity depends on the height of the tree. For the recursive approach, the stack space required is proportional to the height of the tree, O(h). Similarly, in the iterative approach, the stack used explicitly has the same O(h) space requirement. This makes the algorithm efficient for balanced trees and capable of handling edge cases like skewed trees. Finally, it's crucial to consider special cases. For an empty tree, the algorithm should terminate gracefully without errors. In a tree with just one node, the algorithm leaves the node unchanged, as its value is the sum of itself. For skewed trees, whether left or right, the traversal still operates efficiently and ensures correctness. When dealing with left-skewed trees, which resemble a linked list sloping downward to the left, the algorithm processes nodes in reverse order, updating their values one by one as it moves upward. This behavior mirrors the right-skewed case but in the opposite direction. For trees with duplicate values, the algorithm treats each node independently, ensuring the running sum is updated correctly at every step. To solidify this understanding, let's walk through an example. Consider a BST with the structure 4 as the root, 1 as its left child, and 6 as its right child. We start with a running underscore sum of 0 and initiate the reverse in-order traversal. The first node we visit is 6, the rightmost node. At this point, we add 6 to the running underscore sum, making it 6, and replace the value of the node with this sum. Next, we move to the root node, 4, adding its value to the running underscore sum. The new running underscore sum becomes 10, and we update the root node's value to reflect this. Finally, we traverse to the left child, node 1, adding its value to the running underscore sum for a total of 11. The value of node 1 is updated to 11. By the end of the traversal, the tree has been transformed into a greater sum tree, with all node values updated appropriately. After completing the transformation, the resulting greater sum tree has the structure 10 as the root, 11 as its left child, and 6 as its right child. Each node's value now represents the sum of all nodes in the original BST that were greater than or equal to it. This example demonstrates how the algorithm systematically processes the tree, leveraging reverse in-order traversal to calculate cumulative sums efficiently. By maintaining a running sum and updating the nodes in place, the algorithm achieves both time and space efficiency. It handles edge cases like empty trees, single-node trees, and skewed structures seamlessly, ensuring correctness in all scenarios. With this understanding, you can apply the same principles to any BST to transform it into a greater sum tree, adapting the approach as needed for recursion depth or iterative traversal. The given Python solution converts a binary search tree, BST, into a greater sum tree, GST. The GST is defined such that each node's value is replaced by the sum of all values greater than or equal to it in the original BST. The solution defines two classes, TreeNode to represent the tree nodes and solution containing the BST to GST method that performs the transformation. Key steps in the code. 1. TreeNode class. This is a utility class representing a node in the binary tree. Each node contains a value, val, a left child, left, and a right child, right. 2. BST to GST method. This is the entry point for the transformation. It uses a helper method, reverse_in_order, to traverse the tree in reverse in order, right-root-left. 3. Reverse in order traversal. The helper function reverse_in_order updates each node's value in reverse in order sequence. A total variable is maintained to accumulate the sum of all visited nodes. This simulates the greater sum calculation as we traverse nodes in decreasing order of their original values. For each node, the total is updated by adding the node's original value. Then, the node's value is updated with the new total. 4. Base case. If the current node is none, leaf node's child, the function returns immediately. 5. Recursive calls. The traversal starts with the right subtree, greater values, then updates the current node, and finally traverses the left subtree, smaller values. 6. Return value. At the end of the traversal, the modified tree is returned as the result. #### complexity. Time complexity, O, n, where n is the number of nodes in the tree. Each node is visited exactly once during the traversal. Space complexity, O, h, where h is the height of the tree. This accounts for the maximum depth of the recursive call stack. This implementation is concise, efficient, and leverages the properties of BSTs to perform the transformation in optimal time. Here, we start with the definition of the treeNode class, which represents the structure of each node in our binary search tree. Each node has an integer value, and references to its left and right child nodes. In the solution class, we define a private variable total to keep track of the cumulative sum as we traverse the tree. The main method, BST to GST, is where the transformation begins. It initializes total to 0 and calls the helper method reverse in order, passing in the root of the tree. The reverse in order traversal is key to this solution, as it processes the nodes in descending order of their values. The traversal starts by checking if the current node is null, in which case it simply returns, ensuring no further processing occurs for non-existent nodes. Next, we move to the right subtree of the current node, as it contains the larger values in a binary search tree. Once the right subtree has been processed, we update the total variable by adding the current node's value to it. This cumulative total is then assigned back to the node's value, effectively transforming it into the greater sum value. After updating the current node, the traversal proceeds to the left subtree, which contains the smaller values. This ensures that each node is visited in descending order of value, and by the time we reach a node, all greater values have already been accounted for in the total. This method guarantees that the tree is correctly transformed into a greater sum tree by the end of the traversal. Here, we start with a simple binary search tree that has 3 nodes, 4 as the root, 1 as the left child, and 6 as the right child. The goal is to transform this tree into a greater sum tree, where each node's value is updated to the sum of all values greater than or equal to it in the original tree. We initialize a variable total to 0, which will keep track of the cumulative sum as we traverse the tree. The traversal follows a reverse in order pattern, meaning we visit the right subtree, then the root, and finally the left subtree. Starting with the right child of node 4, we visit node 6. Since it has no right child, we update total by adding the value of node 6, which makes total equals 6. Then, we update the value of node 6 to this new total. The tree structure itself remains the same, but node 6's value is now updated to 6. Next, we return to the root node, which is node 4. At this point, the total is 6. We add the value of node 4 to total, updating it to 10. Then, we set the value of node 4 to the new total, so node 4 now has a value of 10. Now, we move to the left child of node 4, which is node 1. Here, we add the value of node 1 to the current total, updating it to 11. The value of node 1 is then updated to this total, so it becomes 11. At this stage, all nodes have been processed, and the tree has been successfully transformed into a greater sum tree. The updated tree has 10 as the root, 11 as the left child, and 6 as the right child. This is our output for this example. Now, let's consider a slightly larger binary search tree with node 5 as the root, node 2 as the left child, and node 13 as the right child. We again initialize total to 0 and perform a reverse in order traversal. Starting with the right child of node 5, we visit node 13. Since it doesn't have a right child, we add its value to total, which makes total equals 13. We then update the value of node 13 to this total. At this point, node 13 remains the right child of node 5, but its value is now updated to 13. We now return to the root node, which is node 5. The current total is 13, so we add the value of node 5 to it, updating total to 18. We then update the value of node 5 to this total, so its value becomes 18. Next, we move to the left child of node 5, which is node 2. Here, we add the value of node 2 to the current total, updating it to 20. The value of node 2 is then updated to this total, making it 20. With all nodes processed, the tree is now transformed into a greater sum tree. The root node has a value of 18, the left child is 20, and the right child is 13. This is the final output for this example. In this edge case, we have a binary search tree with only one node, which is node 3. Since there are no other nodes in the tree, the reverse in order traversal simply processes this single node. We initialize total to 0 and add the value of node 3 to it, updating total to 3. Then, we update the value of node 3 to this total. Since there are no left or right subtrees to process, the tree remains the same, with node 3 as the root. The output for this edge case is a tree where the root node has a value of 3. The algorithm's efficiency lies in its use of reverse in-order traversal, which processes nodes in descending order of their values. This ensures that the running sum, stored in the total variable, always includes the values of all previously processed nodes. For each node, we first traverse its right subtree to handle larger values, update total to include the node's value, and then modify the node's value to reflect the updated total. Finally, we traverse the left subtree to process smaller values. This approach ensures that the tree is transformed into a greater sum tree in a single traversal, adhering to the constraints of the problem. The use of a cumulative sum and the descending order of processing make this method both intuitive and efficient. The time complexity of this algorithm is O(n), where n is the number of nodes in the binary search tree. This is because the algorithm performs a single reverse in-order traversal of the tree, ensuring that each node is visited exactly once. Let's break this down further. The reverse in-order traversal involves recursively visiting the right subtree, updating the total variable and the node's value, and then traversing the left subtree. Since each of these steps operates on one node at a time and involves constant time operations like addition and assignment, the total cost is directly proportional to the number of nodes in the tree. Other operations, such as initializing the total variable and making recursive function calls, are also constant time per node and don't contribute additional complexity. Therefore, the time complexity of the algorithm is O(n). The space complexity of this algorithm is O(h), where h is the height of the binary search tree. This stems from the memory used by the recursion stack during the reverse in-order traversal. Let's consider the recursion stack in more detail. In the worst case, the stack will hold at most h function calls, corresponding to the height of the tree. For a balanced binary search tree, the height h is log n, which means the space complexity in this scenario is O log n. However, in the case of a skewed tree, where all nodes are aligned in a single path, the height h is equal to n, resulting in O(n) space complexity. It's also worth noting that the only additional memory used is for the total variable, which requires constant space O(1). Therefore, the overall space complexity is determined by the height of the tree, making it O(h). When comparing this optimized algorithm to naive approaches, the improvements in efficiency become clear. A common naive approach might involve performing a standard in-order traversal to store all node values in an array, which requires O(n) space. Then, for each node, the algorithm would calculate the greater sum by iterating through the array, leading to a worst-case time complexity of O(n squared). In contrast, the optimized algorithm avoids storing intermediate data, which reduces space usage to O(h), where h is the height of the tree. Additionally, the optimized algorithm achieves a linear time complexity of O(n), a significant improvement over the quadratic time complexity of the naive approach. Looking at best, average, and worst cases, a balanced BST minimizes space to O log n while maintaining an O(n) time complexity. For randomly structured trees, the height typically remains logarithmic, so space stays O log n. However, in the worst case of a skewed tree, the recursion stack grows to O(n), though the time complexity remains O(n). The time complexity of the algorithm can be mathematically proven as O(n). Each node is visited exactly once during the reverse in-order traversal, and each visit involves a constant amount of work, such as updating the total variable and the node's value. This means the total work is proportional to the number of nodes, O(1), work per node multiplied by n nodes, resulting in O(n). As for space complexity, it is determined by the maximum depth of the recursion stack, which corresponds to the height of the tree. In a balanced binary search tree, the height h is log n, leading to O log n space. For a skewed tree, the height h equals n, resulting in O(n) space. These calculations confirm the algorithm's time complexity is O(n), and space complexity is O(h), where h is the height of the tree. One common mistake when solving this problem is failing to fully account for the properties of a binary search tree. Remember, in a BST, the left subtree contains values smaller than the root, and the right subtree contains values larger than the root. Treating the tree as a generic binary tree without leveraging this sorted structure can lead to inefficient solutions. For instance, a brute force approach might involve recalculating sums multiple times, leading to an unnecessary time complexity of O(n) squared, whereas using the BST properties allows us to achieve an optimal O(n) solution. Another issue arises with incorrect traversal order. To transform a BST into a greater sum tree, we must process nodes in descending order, which is achieved with a reverse in-order traversal going from the right subtree to the root, and then to the left subtree. If you mistakenly use in-order traversal, the cumulative sums will be calculated incorrectly. Lastly, modifying node values directly during traversal can cause problems. Once you overwrite a node's value, you lose the original data, which might still be needed for subsequent calculations. This can lead to subtle bugs and incorrect results. Another frequent pitfall is overcomplicating the solution by introducing unnecessary space usage. For example, using additional data structures like arrays or hash maps to store cumulative sums might seem helpful at first, but it increases space complexity. In reality, this problem can be solved efficiently with O(1) extra space by relying solely on the recursion stack. Over-engineering the space usage not only makes the code less elegant but also less efficient. Additionally, it's important not to overlook edge cases. Scenarios like an empty tree, a single-node tree, or trees with very large input sizes can easily be mishandled if not accounted for during testing. Missing these edge cases can lead to runtime errors, incorrect outputs, or inefficient performance in corner case scenarios. Addressing these situations proactively ensures your solution is robust and ready for real-world usage. To succeed in an interview setting, it's crucial to understand the core insights behind this problem. The key realization is that reverse in-order traversal processes nodes in descending order for a binary search tree, which is perfect for computing cumulative sums efficiently. This is a classic example of transforming a BST based on cumulative properties, and recognizing this pattern can help you identify similar problems. Interviewers often look for candidates who can move beyond brute force methods and fully utilize the structural advantages of BSTs to achieve O(n) time complexity and O(h) space complexity, where h is the height of the tree. They also want to see your awareness of edge cases, such as empty trees, single-node trees, or trees with duplicate values. Being able to articulate the trade-offs in different approaches, like comparing iterative methods to recursion, demonstrates a strong understanding. While iterative solutions avoid the risk of stack overflow in deeply nested trees, they typically require more code and careful stack management, which might be harder to implement during an interview. This problem is closely related to several others on LeetCode. For instance, LeetCode 1038, which is the problem we're working on, directly transforms a BST into a greater sum tree. LeetCode 538, convert BST to greater tree, is essentially the same problem but framed slightly differently. LeetCode 230, kth smallest element in a BST, and LeetCode 700, search in a binary search tree, both involve leveraging BST properties, making them great practice for understanding traversal patterns. As for alternative approaches, iterative reverse in-order traversal is a solid option. While it avoids recursion and its associated risks, it does require careful stack management, making the implementation more complex. Brute force methods, on the other hand, are simpler to implement and can be a good starting point for understanding the problem, though they are far less efficient with a time complexity of n squared. Finally, you could explore augmenting the tree with additional data, such as storing cumulative sums at each node. This approach is useful for answering similar queries efficiently, but it comes with trade-offs in terms of increased space complexity and pre-processing time. Understanding these alternatives allows you to choose the right approach based on the specific constraints and requirements of the problem. Great job! We've completed problem number 1038, binary search tree to greater some tree. We summarized the efficient approach, discussed its time and space complexities, and highlighted key takeaways. Remember to practice similar problems to strengthen your understanding. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!